On the test, you won't have to solve a multi-loop circuit in the full extent that we've done before, but you will have to be able to understand how to write the loop rules and the junction rule for a multi-loop circuit. And when given a certain amount of information, that is, so that you don't have to solve the full system of 3 equations, be able to solve for one of the current. So here are some examples of that. Here's just a quick test. You'll see some others like this in the concept test, which we'll take on the online quiz. Which of the following equations for this circuit is correct? So for each of these, like for example, you'll need to pick the first component. So for example, right here, it starts at -6. That means I'm going to be going in this direction. And then you follow throughout the circuit and ask yourself, well, is this correct? Do I have all the correct signs and all the correct elements? So I'll leave that for you to try on your own. And then, given that you know some of the information, such as, for example, here, I give you I2, which is 2.45 amps in this direction. What is the magnitude and direction of I3? And then in that, you'll need to figure out, well, am I going to apply the loop rule or the junction rule? And if I apply the loop rule, to which loop am I going to apply it so that I can find the magnitude and direction of the current I3? I'll let you try those on your own. And here's another asking for the magnitude and direction, or the magnitude rather, of the current I1. Now, if you choose the appropriate loop for this one, it becomes very trivial, this problem. But if you choose the wrong loop, then it becomes quite difficult. So I'll leave that for you. And here's another. Choosing the appropriate equation. 3 of these equations are incorrect. Only 1 is correct. All right, now let's move on to our next topic, which is in resistor-capacitor circuits. In circuits with capacitors, the current varies with time. After a circuit is turned on, the capacitor is charging, and the current is waning, is becoming less. So if you have an RC circuit, that is a circuit that looks like this. You initially have a very big current until that capacitor is charged, and then the current basically goes to 0 when the capacitor is charged. So you have a big current through the resistor until the capacitor is charged, and then you get a smaller and smaller current until there's no current at all. There's a picture of an RC circuit. When the capacitor is fully charged, then the charge on the capacitor is equal to CV, just like we had before. So here, it's not really much different than what we've done before, except now we're adding a resistor, and we're also going to characterize how that charge changes. So as you're charging a capacitor, the charge gradually accumulates on the capacitor, and it does that in a particular way. The way that it does it is an exponential function. So the charge on the capacitor, that is Q, this is going to be Q as a function of time, is going to equal the total charge, that is this charge. What is the charge on the capacitor when it's reached its full capacity, times this function, 1 minus E, which is the exponential function, to negative T over RC. So that charge gradually increases as time goes on. I'll plot this in just a second, but let me go ahead and do it here. So I have Q versus T. This function looks like this, and it approaches the point where Q equals big Q, your total Q. Similarly, our current follows a similar thing. The current is going to be V over R times e to the minus t, over RC. And here's a plot of the current. So initially we have a big current, which is equal to V over R, and then as time goes along, that current goes down to 0. So when the capacitor is fully charged, there is 0 current. When fully charged, there is 0 current. Because you already have all the charge that you can have on that capacitor. It's fully charged, so you don't need any more. The current actually takes charges to the capacitor. After you charge a capacitor, the battery can be removed and the charge stored by the capacitor can be used at a later time. If you remember the boost pack that we saw, that's what was happening there. The boost pack was where the fellow was using the capacitors for his car battery. He was charging up the capacitor with the alternator in the car, and then was able to use that charge for later. A discharging circuit will look like this. So I can take that charge and save it for later, and then when I want to use it, I don't need the battery anymore. So that battery can go away, and I have a circuit that looks like this. It's an RC circuit, but no battery. And then as I discharge it, so as I close this switch, the current, the voltage, and the charge are all going to decrease with time as an exponential function. So the charge now is going to be Q equal e to the minus t over RC. So if you recall, this is the same function that we had for current, but now we have it for charge, and it's going to look like this. It's going to start with a charge Q, and then it's going to gradually go down to 0. The current is going to be V over R, e to the minus t over RC. So this charge, as it's leaving the capacitor, is going to travel through the wire, and as you might expect, that current will decrease with time. If you recall when we watched the video with Colin on MakeZine for capacitors, he showed the LED being the capacitor being discharged through the LED. If you remember, the LED was really bright, and then it got dimmer, bright, and then dimmer. And that's what when a capacitor discharges, it initially has a large current equal to V over R, and then that current gradually goes to 0. So it's bright, the LED is bright, and then it dims, and eventually goes out. We can also write an expression for our potential. It's just going to be V naught. That is going to be the maximum potential, e to the minus t over RC. And all of these, as I've sort of sketched here, follow this function, right? That initially these things are equal to either the total charge, the maximum current, or the maximum potential, and then they discharge with time. Bright, and then dimmer. They discharge with time. Right, this is really useful when you are building circuits that need to have a repetitive thing to occur. So, for example, flashing lights, like the flashing lights on the roadways that they use to mark, where hazards on the roadway or whatever. These flashing lights are in your car. These are very simply created just with a capacitor. You charge the capacitor, and then you allow the capacitor to discharge. Charge and discharge. Charge and discharge. And it's fairly simple to build circuits to do that with very inexpensive capacitors. There are other ways to make these time-dependent circuits, but capacitors are probably by far the easiest. Now, the time for charging or discharging a capacitor is characterized by the time constant for the RC circuit, and this time constant is given as tau. It's equal to the resistance times the capacitance. The units for the time constant are in seconds. And after 10 times tau, we consider the capacitor to be either charged or discharged. So if we go back to this graph, where was it? If we go back to this graph, we would consider this basically to be 10 times the time constant. Basically, that capacitor is fully charged at 10 times the time constant. Now, you can allow it to continue charging. That's the way it is with the exponential function, that you'll continue to accumulate just a tiny, tiny amount of charge, basically out to infinity in infinite time. But basically, it's fully charged at 10 times the time constant. All right? Why don't you try this quick test? This is just sort of a basic thing. You'll need to calculate what is the time constant and then take 10 times that time constant. And now let's consider this circuit. So I want to know, after 20 seconds, what is the current in the 2 ohm resistor? So at t equal 20, what is I? Now the time constant here is 2 seconds. I'm sorry, let me pause for just a second. And so as I said, the time constant for this, we're looking at this part of the circuit. I have two 1 ohm resistors in series with a 1 farad capacitor. The time constant here is going to equal R times C, which is equal to 2 seconds. So the relevance of the 20 seconds is that that's 10 times tau. So after 20 seconds, the capacitor is fully charged. And since the capacitor is fully charged, the current through this branch is equal to 0. So the current through the capacitor is 0. Remember that plot of I versus T looks like this. And at 20 seconds, the current through that capacitor branch has gone to 0. Okay, so now if I want to know what is the current through the 2 ohm resistor, well, this becomes a problem that we've done already, is I want to know, this is my 1 ohm resistor and this is my 2 ohm resistor. Remember, I had that other little branch here, but it's like it doesn't exist because there is no current flowing through that branch. I don't even draw it, so we're just going to get rid of it. So if I want to know the current here, I have a 6-volt battery going through 3 ohms, equivalent resistance. So I is V over R, that's 6 over 3, which is equal to 2 amps. So that's my answer. The point here being that the charge on this capacitor is fully charged, and so it is no longer charging. We're going to carry on and we'll do the next one. Okay, let's consider this circuit. So this is a nice circuit that would show you where you can charge a capacitor and then discharge a capacitor. So here, notice in this circuit that we have 2 switches. We have a switch up here up top, and then we have a switch up bottom. Now, after 5 seconds after closing the bottom switch, what is the charge on the capacitor? So here I'm going to close this switch, and I want to know what is the charge on this capacitor. Well, like we had before, I have an equivalent here of 2 ohms, and so I can find the charge here. So my resistance is going to be 2 ohms. My capacitance is 1 farad, and so I can find my charge Q on that capacitor is going to equal to big Q. That's the maximum Q that it can have, times 1 minus e to the minus t over RC. So this is going to equal C times V times 1 minus e to the minus t over RC. Now let's put in some numbers here. The capacitance is 1 farad. The voltage on that battery is 6 volts times 1 minus e to the minus 5 seconds divided by R times C, which is going to be 2 seconds. So you should practice with your exponential function, but e to the minus 5 over 2, let's see, 5, I get as 0.0821. So let me just put that up here. So you can try it on your e to the minus 2.5 equals 0.0821. Exponential is not a common function that people use, though the exponential function does come up a lot in biological applications, so it's a useful thing to know how to use. And if I do this full calculation, I get 1.84 coulombs. All right, so it's not quite yet fully charged, right, because I can get a maximum of 6 coulombs, but here I'm only about 1/3 charged. But let's figure out, notice I'm only at 5 seconds, but my time constant, tau, is equal to RC, or 2 seconds. So I'm only about 2.5 times the time constant, but it's going to be fully charged after 10 times the time constant, or 20 seconds, when it's fully charged. And when it's fully charged, you will then open this switch, and close the top switch, and then you can have it discharged through this capacitor. And so we can ask similar questions about, well, what is the charge on the capacitor after so much time, or what is the current through the 4 ohm resistor after so much time, using those same sets of equations that describe what is the current or charge or voltage on each individual component. All right, we'll pause there, although let's see, here's another question. You can try on your own. And in the next screencast, we'll move on with household circuits.